The Eurolabs project offers transnational access to more than 40 European research infrastructures and brings together the three scientific communities of nuclear physics, detectors and accelerators for particle physics. The transnational access activities support small teams to carry out experiments and tests at these facilities. One of them is the Jsi-Triga Mark III reactor at JSI in Slovenia.
My name is Vladimir Cindro. I work at the Experimental Particle Physics Department at Jožef Stefan Institute. Since we joined the ATLAS experiment 20 years ago, we are working on the development of radiation-hard detector components, mostly silicon detectors and related electronics. Jsi-Triga reactor is a powerful source of neutrons having a fission spectrum ranging from thermal to several MeV neutrons. It can be also used as a source of gamma radiation when the fission is switched off. With a good knowledge of neutron spectrum and neutron damage factors, the nominal fluence can be translated to the equivalent fluence, allowing scaling to the damage caused by other types of particles. There are several experimental channels which allow fast irradiations of samples with a size of up to few centimeters. Samples are inserted directly into the reactor core and pulled out when the desired neutron fluence is acquired. A new channel for irradiation of larger samples is under construction with the support of
Eurolabs
and will be available for users in the middle of 2016. Neutron fluxes can be scaled by varying reactor power from the highest power, which is 200 kilowatts, to several watts. Fluences as high as 10 to 16 neutrons per square centimeters can be reached in 1 hour. So here you can see top view of the reactor. Here in the middle we have a reactor core which is surrounded by the water tank. The experimental channels are coming from the side to the core and from the top directly from the reactor platform. Samples are inserted to the tubes and they remain close to the core until irradiation is done. Then we pull the samples out of the reactor. After irradiation, they are transferred to the refrigerator to stop the annealing of defects in the samples.
Okay, now we are in a facility called dry chamber. This is a large empty space very close to the neutron core. Over here we have a shutter, a 10 centimeter thick LED, which can be lifted during the reactor operation. And then we have a pretty homogeneous neutron beam 60 centimeters wide and 60 centimeters high. And here we can irradiate larger samples. For example, the whole computer. The wires can be guided onto the reactor platform so we can perform online tests of different electronics.